Hello everyone. Let's study about the atmosphere today. So, what is atmosphere? Atmosphere is an odorless, colorless, tasteless mixture of gases held by gravity. And its origin story matters. It is not just leftover gas from Earth's formation. It is largely a product of volcanic outgassing and later biospheric redistribution. That is why you see water vapor, CO2, and nitrogen coming out through volcanic evolution. One more concept clarity line to lock this in. The atmosphere is a mixture, but it behaves like a single gas because it is thoroughly blended. Now, if you want to understand why Earth is habitable, think of the atmosphere as an invisible shield and blanket working together in Earth's heat budget. Incoming solar radiation is short wave. Outgoing terrestrial radiation is long wave. The filter role is clear. It absorbs harmful UV radiation. The blanket role is also clear. It prevents extreme temperature swings between day and night. Here's a trap you need to be aware of. Greenhouse gases are transparent to incoming short-wave solar radiation, but relatively opaque to outgoing long-wave terrestrial radiation. So memorize it exactly as written. Short wave in, long wave out. And greenhouse gases mainly trap the outgoing waves. With the mechanism clear, let's quickly see what the atmosphere is made of by volume. Nitrogen is 78.08%. It dilutes oxygen and controls combustion. Oxygen is 20.95%, life breath and essential for fuel. Argon is 0.93%, an inert noble gas. Carbon dioxide is just 0.036%, but it is a heat absorber. Most students lose marks here because they misrank the gases. Argon is the third most abundant gas, and it is significantly more abundant than CO2. Do not get this order wrong. Now we zoom into trace gases, because tiny percentages create massive impact. Carbon dioxide sits at about 0.038% of dry air, but it is meteorologically crucial as a heat absorber, and the trend is rising due to fossil fuels warming the lower layers. On the other side is the shield gas, ozone. Ozone is concentrated around 20 to 25 kilometers. It absorbs high-frequency UV radiation, and it is formed at high altitudes and transported down. This is where examiners quietly test whether you can separate heat trapping from UV shielding. Next, the real weather makers are not the big gases, but water vapor and dust. Water vapor is variable from 0 to 4% by volume, and it decreases from equator to poles. It has a greenhouse function too. It absorbs terrestrial radiation and traps heat. And notice the distribution line that matters. About 90% of water vapor is found within the first 5 kilometers. Now particulates or aerosols. Sources include salt, pollen, ash, and soot. They have an optical function, scattering light to create blue skies and red sunsets. And a physical function. They act as hygroscopic nuclei, which is essential for rain. The quick visual takeaway at the bottom is perfect. Equator around 4% vapor. Poles close to 0% vapor. Now that the ingredients are clear, let's divide the atmosphere chemically, not by temperature. From 0 to 80 kilometers, you have the homosphere, a uniform mix. The composition stays the same even though density drops with height. From 80 kilometers up to about 10,000 kilometers, you have the heterosphere, layered by molecular weight. Heavier gases like N2 and O2 are lower. Lighter gases like hydrogen and helium dominate higher up. Here's a trap you need to be aware of. Do not confuse chemical layers with temperature layers. The mix breaks down at 80 kilometers. That is the key marker. Now we move to the temperature-based layers, and we begin with level 1, the troposphere, the weather zone. Its height is about 18 kilometers at the equator and about 8 kilometers at the poles. It contains about 90% of the total atmospheric mass. The normal lapse rate is straightforward. Temperature decreases with height, around 6.4 degrees Celsius per kilometer. And this is where all weather lives: clouds, storms, rainfall. The boundary is the tropopause, where temperature becomes nearly constant. Examiners expect you to connect weather with troposphere, not with the higher layers. Above the tropopause comes level 2, the stratosphere, the ozone home. Altitude goes from the tropopause up to about 50 kilometers. The temperature trend reverses here. It increases with height, an inversion. Why? Because the ozone layer absorbs UV radiation and generates heat. And here's a trick you need to be aware of. Commercial jets often fly in the lower stratosphere to avoid weather turbulence and to utilize more stable horizontal air currents. If you can remember ozone and inversion together, most stratosphere questions become routine. Next is level 3, the mesosphere, the meteor shield. It lies roughly from 50 kilometers to 80 kilometers. The temperature trend again decreases with height. This layer reaches the atmosphere's minimum temperature, around minus 90 degrees Celsius. And the critical function is simple but high yield. Friction burns up meteorites before they can hit the surface. So whenever you see meteors and extreme cold together, your answer should immediately point to the mesosphere. Now we reach level 4, the thermosphere, which is known as the heat paradox for a reason. Altitude is about 80 kilometers to 480 kilometers. Temperature shows a rapid increase, going up to around 1200 degrees Celsius due to solar radiation. But here is the concept hack. Why wouldn't you burn? Because temperature is high in the sense of molecular speed, but heat transfer is low because the density of molecules is extremely low. There are too few particles to transfer energy to your skin. This is also the layer where satellites are commonly associated in basic mapping questions. Alongside these temperature layers, there is a functional zone you must remember: the ionosphere. Its location overlaps the mesosphere and thermosphere, roughly 60 to 400 kilometers. The mechanism is ionization. Cosmic and solar rays ionize atoms, creating charged particles. The key functions are high yield. 1. Communication. It reflects radio waves back to Earth. 2. Auroras. Excitation of oxygen and nitrogen by magnetic fields creates the northern lights. If you link ionosphere with radio reflection and aurora formation, you will not fumble common prelim statements. Finally, level 5 is the exosphere, the frontier. It lies above about 480 kilometers. Composition is extremely rarefied and light gases like hydrogen and helium predominate. The dynamics line is the point. Gravity is negligible, so atoms can escape into space. This is the conceptual bridge between atmosphere and outer space, not a weather layer. Let's lock it with the cheat sheet table, because this is how you revise fast before an exam. Troposphere. Temperature decreases. Key feature is weather and lapse rate. Stratosphere. Temperature increases. Key feature is ozone and jet streams. Mesosphere. Temperature decreases. Key feature is meteors and minus 90 degrees Celsius. Thermosphere. Temperature increases. Key feature is satellites and the heat paradox. Master the transitions, because this table alone covers a major chunk of structural exam questions, and you are exam ready.